Section 8.12 Ultracomputers. Quantum computers are not made for evaluating expressions, today, but let's suppose that this is merely a technical problem. Suppose that in time there will be hybrid computers that combine the calculating power of supercomputers with the parallelism of quantum computers. Let's call these ultracomputers. What can Sandra do today to prepare for the time when Emily has an ultracomputer? We can take a cue from the way we defeated Grover's algorithm, section 18.6. We expanded the size of the key to exceed the capability of the algorithm. This can also be done with ultracomputers. We can increase the number of unknowns that the computer needs to deal with beyond whatever capabilities you estimate the ultracomputer may possess. Let us look at two aspects of this: substitution and random number generation. These algorithms will require extremely large encryption keys. Let's simply accept that in the future world where ultracomputers exist, such huge keys will be manageable. Section 18.12.1 Substitution. If a substitution is not defined by some mathematical rule, then it can be defined by a substitution table. Each entry in the table is a value known to Sandra, but unknown to Emily. Each table entry can be regarded as a variable in the mathematical sense. Initially, each variable can take on any value. If Emily learns some of these values, that narrows the choices for the other variables, but initially any character could substitute for any other. Sandra's objective is to overwhelm the capabilities of the ultracomputer. A general polyalphabetic cipher has a 26 by 26 tableau for hand use, but a 256 by 256 tableau for computer use. That provides 2 to the power 16, or 65,536 unknown values. There is, however, no reason why you should limit yourself to 256 rows in the tableau. If Emily has an ultracomputer, it is reasonable that Sandra also would have a computer with high speed and large memory. Sandra could use a tableau of 1024 rows with 10-bit keys, or 4096 rows with 12-bit keys, or even 65,536 rows with 16-bit keys. That requires 2 to the power of 24 equals 16,777,216 bytes of internal storage for the substitution table, well within the capacity of current personal computers. Plus, having a 16-bit key for an 8-bit substitution provides a very desirable redundancy. Let's call the 2 to the power 24 element tableau tab 24. Each row of tab 24 has its own mixing key. If this mixing key has 256 bits, then the entire tableau has 256 times 65,536 equals 16,777,216 key bits. It is also feasible for Sandra to use a full bigram table. A 256 by 256 bigram table using an 8-bit key to select a row, actually a layer, would require 2 to the power 25 equals 33,554,432 bytes of internal storage. Again, this is feasible today. It would require a much larger computer if the tableau had 65,536 layers and 16-bit keys. Remember, however, these substitution tables must be kept secret, and they must be fully random. Even if they are generated by some algorithm, it must be absolutely beyond the capability of Emily's ultracomputer to determine the initial state and parameters of the generator. See section 13.13 for some relevant methods. Section 18.12.2 Random numbers. The methods of section 13.13 are a good start, but to produce a pseudo-random number generator that will stand up to an ultracomputer, we combine the concept of a selection generator from section 13.11 with the techniques for refreshing the generator in section 13.15. The ultra generator UG, pronounced HUG, uses three arrays, A, B and C. Arrays A and B each contain 65,536 entries that are 24-bit integers. Array C contains 2 to the power 24, or 16,777,216 entries that are 8-bit integers. The three arrays can be initialized from nature photos, as described in section 13.14.2. Sandra and Riva must have identical arrays. The generator produces an 8-bit output in each cycle. Cycle n consists of these steps. 1. Calculate x equals an plus an minus 103 plus an minus 1071 mod 16777,216 and replace an by x. 2. Reduce x equals x mod 65536 and set y equals bx. The output of the Hugh generator on this cycle is cy. 3. Replace bx by bx plus bx minus 573 plus bx minus 2604 mod 16777,216. 4. Replace cy by cy plus y minus 249 plus cy minus 16774 mod 256. The subscripts wrap around the modulo 65536 or modulo 16777,216 as appropriate. There is nothing special about the lags 103, 1071 up to 16774. I did not test to see whether these values produce especially long periods. With such huge seed arrays, even degenerate periods will be extremely long. You may use any of the combining functions of section 13.1, such as MAD or lagged linear addition from section 13.14.1. When you refresh these random numbers, the two methods of section 13.14 are not sufficient when your opponent has an ultracomputer, but they can be combined to make a strong refresh function. Each time you refresh, you will need a new random array R of 65,536 or more 24-bit integers. Let the lengths of A, B, C and R be LA, LB, LC and LR. Here, A equals floor of LC over LR minus 1. The notation floor LC over LR means the greatest integer not exceeding LC over LR. For example, floor of 8 over 3 is 2, and floor of 9 over 3 is 3. The effect of using CAN instead of CN is to spread the bytes of R evenly throughout the C array. These two steps should be repeated 3 or more times. As always, the subscripts wrap around. By the way, there is no requirement that the size of the C array must be a power of 2. LC could be, for example, 77,777,777, in which case the A, B and R arrays would need to contain integers modulo 777, 77777, and the modulus 16777,216 would be replaced by 777,77777 in the calculations above. The only limits on the size of LC are the amount of storage you wish to use and the practicalities of distributing such a large key. These two techniques, substitution and random number generation, can be combined to make any number of block and stream ciphers that will withstand ultracomputers. The next two sections illustrate one cipher of each type.